with angular position, velocity and acceleration. Nedir bu? Çarkıfelek mi? Wheel of Fortune in English. So an example, the initial angular velocity of this wheel is given. If you have watched this show on TV, people are given an initial velocity, but after a while it stops, right? Because it has a negative angular acceleration. So it stops after 1.25 revolutions. And the question is, what is the angular acceleration? Of course. And initial angular velocity is given as 3.4 radian per second. And second question is, how long does it take for the wheel to come to a rest? That is the time. So there are many ways to solve the problem. Since we know the initial and final velocities, and just like we had a similar equation in kinematics, remember v final square minus v initial square plus 2a times delta x. So in rotation, we have these quantities which corresponds to velocity, angular velocity, and the angular acceleration, and as the displacement, the total angle which is traveled by the rotation. So from this, you can easily, this is implied in the question, final velocity is not given, but of course when it stops, the final will be 0, so put 0 in here. Omega 0 is 3.4, and delta theta is given, the total angular displacement. It is given in terms of revolutions. Of course, you have to convert this to radian. So we know that 1 revolution is 2 pi radian, and then 1.25 revolutions is 2 pi times 1.5. So when you put everything in the equation, solve for alpha, which is the angular acceleration, you will have a negative quantity, which is minus 0.74 radian per second square. So this is the angular acceleration. It is negative because the wheel is slowing down. The next is to find the duration, the time from which this initial velocity to get zero velocity. For this, again, you can use this initial and final velocities plus angular velocities plus alpha times t. So it is very easy to solve for t, and you know initial acceleration, initial angular velocity is given minus plus 3.4. This minus comes from the equation, but we have also minus angular acceleration, so this total time must be always positive to make sure that you never get t is equal to minus, right? T will never get a minus quantity. So if you somehow get a minus quantity, then it's doing something you are doing wrong. So you find the time for stopping the wheel is 4.6 seconds. Okay, so just application of these kinematics equations. Another question, it is helpful for you to solve more questions, of course. A ball is spinning about an axis that passes through its center, and the constant acceleration is given as pi radian per second square. So let's immediately write down the acceleration as alpha, the angular acceleration. It is pi. And during a time interval from an initial time t1 to t2, a final time, the angular displacement is also given as pi radians. So delta theta is given. Again, it is pi, right? At time t2, the angular velocity of the ball is given. Let's call this angular velocity omega 2, because it is given at time t2, and it is 2 pi. Let's write down the units, radian per second. This is radian, and this is radian per second square. The question is, what is the ball's angular velocity at time t1, at the initial time? That is omega. What is omega 1? So what kind of equation should I use? It is obviously a constant accelerated motion, but everything is in angle, not linear distance, but in terms of angle. But we have the same forms of equations, right? You have theta is equal to theta 0 plus omega 0 times t plus 1/2 alpha t square, right? And you have another equation for the final angular velocity, omega 0 plus alpha times t, and etc. We have also this angular displacement. If you have, if you have a constant acceleration, and if you know the initial and final angular velocities, then the angular displacement can be written as theta 0 plus 1/2 omega plus omega 1, omega 0, initial and final and initial angular velocities times t. So you can use these equations. Which one is best for us? The shortest one. The definitions of these sub-zero values, for example, theta in here is the final point in angle. This is the initial value. This is initial velocity. This is constant acceleration. Final angular velocity, initial angular velocity, final position in angle, in rotation, initial angle, right? But you are given somehow t1 and t2. And initial time is not 0. Okay? So what to do? If you have initial time is 0, then it is very obvious that if you put t is equal to 0 in this equation, you will get theta is equal to theta 0. So for these equations, we assume that the initial time is 0. But if you don't have, if you have the initial time t1, which is not specifically equal to 0, what to do? The equations will be in the same format. Okay. So instead of theta and theta 0, instead of omega and omega 0, you can say theta 2, theta 1, omega 2, omega 1, but the format of the equations will be the same. So you can write, let's do this for the third equation. Since this is the final angle, and this is the initial angle, this is the final velocity, this is the initial angular velocity. So I can write theta 2 is equal to theta 1 plus 1/2 omega 2 plus omega 1 times, what is t in that case? T2 minus T1, right? Because T is T minus 0. So if you reformat or rewrite your equation with the given values in problem, so the rest is easy. Just because delta theta is always the final value minus initial value. So delta theta in our problem is nothing but theta 2 minus theta 1, right? So you can reformat this. Theta 2 minus theta 1 is equal to 1/2 omega 2 plus omega 1, right, delta t. Instead of T2 minus T1, you can write delta T. So this is given in the problem. This is pi, right? And you are given omega 2, right? The final velocity, right? You are not given omega 1 because omega 1 is asked to find. And what about delta theta? Delta theta also you don't know. So you have to use the second equation, right? And the second equation, you can use this one. Omega 2 is equal to omega 1 plus alpha times T2 minus T1, but you can write delta T. So I can solve this for delta T, and I can put whatever the delta T in here in terms of omega 2, omega 1, and an alpha, I can substitute in here. Then I will get an equation with one unknown. So omega 2 minus omega 1 divided by alpha, right, is equal to delta T. So instead of delta T in here, let's write omega 2 minus omega 1 divided by alpha. Now you have only one unknown, right? Because, and we can rewrite these 1/2. We have a multiplication of omega 2 plus omega 1 and omega 2 minus omega 1, which is equal to omega 2 squared minus omega 1 squared, right, divided by alpha. So omega 2 is given. Omega 2 is 2 pi. It is 2 pi, of course, squared. It is 4 pi squared. And we don't know alpha, omega 1. We know what alpha is. It is pi. So from this, you can easily write, you can find omega 1 is equal to, in square root, 2 pi. Okay. Anything which is not clear? So it is not always given the initial time as 0, but you may be given different times, and in that case, this is how you reformat your equations. So, so far I have given the definitions of angular variables, which is angular displacement, angular velocity, angular acceleration. And we already know the linear quantities, linear velocity, linear acceleration. This is something we know from the second and third chapter. The question is, what is the relation between these quantities, the linear and angular quantities? And this can be best explained by considering this merry-go-round atlı karınca. Suppose you have this boy having a fun time on this merry-go-round, and of course circulating. When he's circulating, it has a linear velocity, right? Because it goes around this circle, and it is a distance, okay? It takes a distance over some time. So you may define it, of course, linear velocity. But if you think one revolution, the duration for one revolution, there is a specific name for that. What is it? The time for one revolution is period, right? And we denote this as capital T. So in one revolution, he takes 2 pi r distance, because if he rotates a circle of radius r, then the circumference of this radius, or the total distance it takes, is 2 pi r. If you divide 2 pi r by time, you will find the linear velocity, his linear velocity. But if you look closely, this equation, 2 pi times r divided by the capital T, which is period, and we know that 2 pi divided by capital T is nothing but the angular velocity, right? That I have given last lecture. It is the angular velocity because in one period, it takes 2 pi angle, 2 pi radian. So this is the definition of angular velocity. And you multiply this by r, the radius, you will get the linear velocity. So linear velocity is related to the angular velocity by just this simple equation. V is equal to omega times r. Okay? And r is, of course, since we are dealing about the rotation, r should be the radius of the rotation. Okay? And of course, we call this tangential velocity. Okay? Well, it's like something different name, but it's linear velocity, in fact. Why we call tangential velocity? Because this velocity, if you think as a vector, it is always tangent at every point. It is tangent to the circle. That's why we call tangential velocity. But it's in fact it's a linear velocity. All right. So immediate example on this. The Earth, which has an equatorial radius of 6,380 kilometers, makes one revolution on its axis every 23.93 hours, not 24 hours. One day is not exactly 24 hours. So, by the way, you learned that one day takes this much hour. What is the tangential speed of Nairobi, which is a city in Kenya? And it is very close city to equator. So this point on the city on the rim of the equator makes one revolution, right, in one day, or 23.93 hours. How can you find the tangential speed of the whole city? In space, of course. Well, since the radius is given, everything is very easy. V is equal to 2 pi times, the radius is 6,380. It is kilometers, so times 10 to 3. Now it's in meters because you have to find the velocity in meter per second. And you have to convert this much hours to seconds. What is number of seconds in 1 hour? 3060. So if you do this calculation, you will find. Really? Okay. And I'm leaving this example to you. You can work it at home. It's again simple. The next, of course, there is not only one relation between the angular velocity and angular acceleration. Also, we have this centripetal acceleration. Remember, we have dealt with this centripetal acceleration in chapter 6, the applications of Newton's law. You think a uniform circular motion, the object is rotating around a circle with a constant speed. It does not change the speed, but it's changing the direction of the velocity, right? In that case, even if there is no change in speed, since the direction of the velocity is changing, we have calculated, or we have given that there must be an acceleration, and this acceleration is centripetal acceleration. If something is rotating with a constant speed, this motion has the centripetal acceleration, and which is given by the speed square divided by r. And since I know now V in terms of omega and R, I can replace here V as omega R, and if you do this, the centripetal acceleration may be expressed in terms of angular velocity of the uniform circular motion. And it is the square of the angular velocity times R. So that means different points of a rotating platform will have different accelerations, right? If the points are having different distances to the origin. If R is large, right? For example, you see two boys in here, two child. One is closer to the center, and the other one is on the rim. Which one has if they both move together on this platform, which one has a larger acceleration, centripetal acceleration? The red one, right? Because R for him is larger. They both have the same omega. Their omega is the same. Okay? Because in equal times, they take equal angles. So they must have the same omega. But since their positions, the radius are different, their accelerations will be different. Any questions? But on the other hand, if the speed of the rotation is also changing, okay? If the speed of the rotation, it may be increasing or decreasing, like in the case of Wheel of Fortune, you will have, again, another acceleration. As I said, this acceleration in terms of the theta is nothing but the angular acceleration. But if you multiply this by R, the radius of the motion, then you will get the tangential acceleration. Remember, the centripetal acceleration is always towards the center. It has any component which is tangent to the circle, or which is tangent to the path rotated by the object. So we have two kinds of linear acceleration in a rotational motion. One is centripetal acceleration. Moreover, if your velocity is changing over time, then you will have a tangential acceleration. And this tangential acceleration is given by alpha times R. Alpha is the angular acceleration. So the total acceleration in a rotating object has two components. One is centripetal acceleration, which is R times omega square, and the other is tangential acceleration, which is R times alpha. Alpha is the angular acceleration. So pictorially, you see if this boy is rotating, but if the platform also is increasing its speed, in the rotation speed, then you have a component which is tangent to the motion. This will be tangential acceleration. And since it's a circular motion, you always have this centripetal acceleration. And the total acceleration will be something like this, because the acceleration is a vector. So to find the total acceleration, I must add these quantities vectorially. Not algebraically, but vectorially. Okay? So for a increasing speed of rotation, the total acceleration is something like this. If the speed will be decreasing, then the acceleration would look like this. Let me draw it. If you had a decreasing speed, the acceleration, total acceleration, will look like this way. Even if he's going in this direction, the acceleration will be like this, if the speed is decreasing. Okay? An example, microhematocrit. It's a device. It's a rotating device which has tubes attached to a center, and this is usually used in laboratories in the hospitals, and it is used for mixing blood or for separating some matter inside the blood. When you rotate this, the tubes, if you have something like blood in the tubes, they will experience a very large acceleration. If you rotate this device very large in large speeds, like in this example, 11,500 RPM. It's a huge speed, right? RPM is, what is RPM? RPM.
Revolution per minute.
Yes. It is another unit for angular velocity. Usually we give angular velocities in terms of radian per second. This is in SI unit system, but most of the time for engines like electrical engines or cars engines, it is given in terms of RPM. So it's huge speed. We can easily convert this to radian per second to appreciate what the strength or magnitude of speed. So with this huge speed, if also the radius is given, radius is 9.0.7 centimeters, which is the bottom of the tube to the center. So the bottom part of this blood will experience very huge centripetal acceleration. If you hand the tube like this, it will be bottom. This part is bottom. Okay. Burası ağzı, buradan takılıyor. Bu tarafı da tüpün alt kısmı oluyor. Ama yatay düzlemde dönüyor. Doesn't matter if it's rotating in the horizontal plane, but it will experience a centripetal acceleration. So what is the centripetal acceleration at the bottom, and what is the linear speed at the bottom of the tube? You can easily use this relation between the linear quantities, and first you can to find the linear speed at the bottom, you multiply omega by r. But since omega is given in terms of RPM, you can convert this first to radian per second, and this much RPM is 1 revolution divided by 60 seconds, but instead of this revolution you will put 2 pi, because 1 revolution is 2 pi, and 1 revolution takes 1 minute takes 60 seconds, so minute is given in here. So at the end you find the linear velocity of the bottom part of the tube as 109 meter per second. And let's calculate the centripetal acceleration by using this. You can either use v square over r, since you already calculated v, or you can use omega square times r. And in both ways you will find the same quantity. It is 131,540 meters per second square. Okay, if you divide this by G, 9.8. Let's take this as 10, G as 10. You will appreciate the largeness of this acceleration. It is around 13,000. It is around 13,000 G times 10 to 3. Okay. Yes.
Revolution per minute is say omega 11.5. It means in a minute it turns
1 revolution, 2 pi. In 1 minute goes one rotation on 2 pi.
How became
Hı?
1 dakikada 15 kere.
1 dakikada 11.500 kere dönüyor. O virgül şey. Yani şey değil. Ondalık kısmı değil. Yani tam 11.500. Bu 130.000 13.000 G. 13.000 G ivme ne yapar biliyor musunuz? Kanı içerisindeki sıvıdan ayırır ve üst tarafta beyaz bir serum kısmı kalır. Kanın beyaz kısmı serumdur aslında. Hani hastanelerde serum takarlar ya. O serum aslında kanın hemoglobin falan hemoglobin kısmının, o kırmızı rengi veren kısmının alınmış halidir. Ne kanıdır o? At veya ineklerden alıyorlar. Besin maddesi var içinde. Bu kadar hızda işte yani aslında bu tür şeylerde o serum bu tür platformlarda hazırlanıyor. Normal kan alınıyor. Çok yüksek hızlarla döndürüldüğü için. Tabii kanın içerisindeki rengini veren kısımlar ağır olduğu için sıvıdan o dibe çöküyor. Okay. So saat kaç? Ha? Instead of break, let me go a little further and I will stop for today. Okay. What do we have? Okay. Rolling motion, it's an interesting part. So far, I have given only rotating objects, and these objects are not translating in space. They are rotating fixed at one point, okay? There is no translational motion. But if you think this bike wheel, and if you rotate it on the ground, if you give a push, it will do two kinds of motion. One motion is a rotation around its center. The other motion is translation. Okay, translation motion. The wheel itself, the center of mass of the wheel itself, will move with some velocity. So, if you throw this wheel with a speed of v, let's say the speed of the center is given by this v, and it goes a distance, you can easily find the speed by observing its distance for one revolution. When the wheel makes one revolution, that's when this point goes around, by the way, the wheel will go toward right, and it comes to the same point on the ground again, okay, here. It goes a distance of 2 pi, right? 2 pi r, because the circumference of the wheel is 2 pi r. And I can divide this by time to find this linear speed of the center of the wheel. 2 pi I divided by t. But again, I know that 2 pi divided by t is the angular velocity of the wheel, because it's rotating, right? So I just found the relation between the speed of the center, the translational speed of the center, and the rotational angular velocity of the wheel. Okay? So if you throw a wheel with some speed, v, and this speed will nothing be a multiplication of the rotational angular speed, rotational speed of the wheel, times the radius of the wheel. So when you rotate an object on the ground, you cannot avoid that these velocities will be relating to each other like this. Okay, the angular velocity must be equal to the angular velocity times the radius must be equal to the linear speed of the object. So, if I ask you momentarily, what will be the linear speed of this point, right top of the wheel, when it's going with a linear velocity of v on the ground. The wheel is rotating, right? Momentarily, when you fix time, this point will have a tangential speed, right? In this direction. Because every point on the wheel has a tangential speed, and right at top, this tangential speed will be parallel to the ground. What is this tangential speed? Is it v? The tangential speed of the center of the wheel, or larger than v, or less than v? It is rotating, it's going right at top. The point has a speed, linear speed. What is the speed? Okay, you can do this. When the wheel is going toward right, you can decompose the motion of the wheel into two parts. One, the wheel is rotating. The other is the wheel is not rotating, but its all points are going toward right with the same velocity. So the motion is sum of these two different cases, right? The motion of the wheel. If everything, if the center goes with a v, every point, if the wheel is not rotating, must go with the same v, right? If the wheel is not rotating. Now, you add the velocities at every point on the rim by superimposing these two pictures, okay? Since the wheel is rotating, if you don't think that it is going, fix it is rotating, the top part, this point, must have a velocity of v, which is omega times r, right? But also, if the wheel is translational motion, if the wheel is in translational motion toward right, everything is going with the same velocity, you must add another v, right, to this point on the rim. And so, when you look at the picture, the complete picture, the wheel is rotating and it's going toward the right direction. This point on the rim must have twice the linear velocity of the center. Am I right? Or is it clear? First, what I have done is, if the center is going in this direction, I have just found what should be the omega, the angular velocity of the wheel, because it's rotating. And this omega is nothing but v divided by r. If the center is going with velocity v, then any point on the rim must have the same velocity v. Okay? And if you think the top point, then since top point is rotation is in the clockwise direction, this direction, the top point has two velocities. One is translational velocity, which is v, and the other is rotational velocity. It's coming from the rotational motion. It's 2v. What about the bottom point? The linear speed of the bottom point. Momentarily, it's 0. However, how fast is your wheel is going? The point of the wheel where it touches the ground is 0 velocity, has 0 velocity, okay? So this point, 0 velocity, because if you see the rotation only, from the rotation, the linear velocity in this part must be in the negative x direction. But the wheel is translating toward right with the same velocity v. So if you add these two velocities, this one and this one, it makes 0. You can think that way. If this point wouldn't have a 0 velocity, then the wheel will skid, right? The wheel will skid means it will slide. Patinaj yapacak veya değil mi? Kayacak. İki nokta arasında bir sürtünme var. Bu çok ilginç bir şey ama bütün hem dönen hem de ilerleyen tekerlekler için durum aynı. Sürtünme kuvvetinin olup olmaması önemli değil. Burada sürtünme kuvveti elbette ki var. Sürtünme kuvveti olmasa zaten hem dönüp hem de ilerleyemez. Sürtünme kuvveti olmasa sadece olduğu yerde döner. Ha. Zaten ilerlemesini sağlayan şey sürtünme kuvveti. Ama buradaki sürtünme kuvveti statik sürtünme kuvveti mi yoksa kinetik sürtünme kuvveti mi? Tekerleğin yere değdiği noktadaki sürtünme kuvveti statik mi kinetik mi? Niye? Çünkü yüzeyler birbirine göre farklı hızda gitmiyor. O yüzeyler birbirine göre farklı hızda gitmiyor. Değdiği noktada zaten o nokta sabit. Ha. So at this point of the wheel, the kind of friction between the wheel and the surface is static friction. Okay, you think about this, and I will stop here. It's a very interesting point, and we will continue on Thursday. So Wednesday is no class, and Thursday we'll continue. 1 hour on Thursday.